So I did the first problem with the spinning ballet dancer. We're given the rotational inertia for a 0.4 and the time of 0.6 seconds, and then r is 0.2 meters, w is 1 rev per second. So first I found the angular acceleration using this formula. A equals the change in w over the change in time. So this would be 2 pi over 0.6 seconds, which comes to about 10.47 rad per second squared. And then the second step was to find the torque, T, which is, to do this I've used the rotational form of Newton's second law, which is I times A, and this comes to 4.4 kilograms times meters per second times what I just calculated, 10.47 rad per second squared. When I did this, I got 46.07 newtons times meters. And then I found the force, which is using the formula T equals R times F, but then you rearrange it to be T over R. And so it's 46.07 newtons times meters over 0.2 meters. And these units cancel out, and it gives us just 230.25 newtons. So this is what the force is. The smallest force which the dancer could push on the ground. And then for the second question, to find the new angular speed, I had these variables I wrote down. So I1 is 4.4, I2 is 1.1, and then W1 is the same period, 2 pi rad per second. And then to find the conservation, I use the conservation of angular momentum, which is L equals I times W. And then we could use this formula to find the missing value W2. This would be I1 times W1 is equal to I2 times W2. So W2 would be I1 times W1 over I2. I plugged in these values, which is 4.4 kilograms times meters squared times 2 pi rad per second over 1.1 kilograms times meters squared. And so the meters squared cancel out, and we're left with 8 pi rad per second. And if you were to do the calculation of 8 pi, it would be about 25.13 rad per second. And so these are the two final answers that I got.